So welcome back. We'll start the afternoon session, and we've got Dan Thompson from Swansea telling us about aspects of E-models or epsilon models. E-models.
Okay, thank you very much, Manuel. Thank you to the organisers. It's a pleasure to be here at this very nice workshop. Apologies, I missed some of your talks yesterday. I hope to catch up on that. But here we go. I'm not sure how much of this title I'm actually going to talk about. I left it quite vague to give me a bit of scope. But since Lucas found these brilliant results on Thursday and Friday, that part of the talk has grown and the other part has shrunk, and we'll see what happens. Okay, so I'm going to talk mainly about work that I've been doing recently with Lucas Scheppers, who is my finishing grad student, and he's here today. And I'll also potentially speak some hints of some work with Alex, who's here, Lewis and Andra, who I don't believe are. But mostly, I think I'll talk about this, but we'll see. So this is a talk in two parts, and they're kind of a bit distinct, so we'll see what happens. So I'm going to talk about resurgent aspects of lambda models. So lambda models are a type of integrable deformation, and that's sort of the topic of this conference, so hopefully many of you know what I'm talking about here. Resurgence is something that's less familiar in general, so I'm going to try and outline a little bit about that, and then apply some ideas of resurgence in the framework of integrability. And I should caveat myself, I'm not presenting you some new conceptual breakthrough here. This is a case study of some techniques that have been developed over a number of years, and there have been a number of recent breakthroughs in the last 12 months, actually, and I'm going to put them all into action on this particular model, and hopefully we can learn something. Okay, so as we all know, perturbation theory is brilliant. Right, you want to calculate the anomalous magnetic moment, so you calculate a vertex, you do a one-loop vertex correction, and you do this for 7 loops in QED, and you get this result. This is, I think, a 7-loop calculation, I think. Amazing. And then you ask the experimentalists to do the to do the experiment, and you find just this incredible precision. So perturbation theory is our bread and butter, and it's amazing. But this should cause sort of cognitive dissonance, because at the same time as it being amazing, it's also fundamentally terrible. So in general, perturbation theory is an expansion in some coupling, G, whose coefficients grow. And they can grow for 2 reasons. They can grow just because you have a lot of Feynman diagrams. That's one source of growth. Another source of growth is actually when you do the integrals themselves, that can produce some extra factorial behavior. And, you know, you try and sum a factorially divergent series, and, well, that's not finite. So what do we do? This is a disaster. And typically what we do is we do as many loops as we can calculate, which is probably 7, if you're really strong, and then we stop and walk away. Actually, that's a good idea, because if you kept going, after a certain point, your calculation would get worse, and worse, and worse, and worse. So that's called truncation. But still, we could ask the question is, can we make some formal sense of perturbation theory? And does this actually mean anything? Is there some physics here? So is this terrible disaster physical? And of course the answer is, I'm going to claim yes. And I'm going to claim this is something that you actually know. And this is the idea of resurgence, which is how non-perturbative contributions correct and understand this factorially divergent behavior of perturbation theory. And in this context of quantum mechanics, this is really well established. And really, the question is quantum field theory. Can we make this idea fly at quantum field theory? And that would be giving us a mathematically precise meaning for what quantum field theory is. Okay, so here's a potential, V. It's a double well, which means it looks classically like there's a degenerate ground state. Yeah? The potential's the same in both holes. And then you calculate the wave functions, and there's an even one and an odd one. And helpfully, Mathematica didn't put the label on the left-hand side of the plot to tell you which one's the ground state and which is the first excited state. But that's an exercise in Sturm-Liouville theory, so I'll leave you to convince yourself the answer to that. But what happens is, it's not that there's a degenerate ground state. There's a splitting of energy levels. And the splitting is mediated by tunneling, instanton effects. So, suppose we don't know about the instanton effect, and we just work in one vacuum, and we do perturbation theory. Indeed, here we will find some factorially divergent series. That's what happens. So you do Rayleigh-Schrödinger perturbation theory in that vacuum, work out your energy level, and you find a factorial growth. But the instanton contribution kicks in, and this is a typical instanton fugacity, e to the minus 1 over g squared. The coefficient here is quite important, this coefficient A. So this A here and this A here are the same, and it's twice the instanton action. And it's twice because the tunneling goes from one to the other and back round. Okay? So instanton tunneling lifts the degeneracy. Nonetheless, let's just try and understand a bit better how to examine this series. So I'm going to now teach you for 2 slides the core techniques of all resurgent analysis. So ask questions on these 2 slides because that's a useful thing to learn. Okay, so we're going to use a technique called Borel summation. Now, I'm going to jazz things up a little bit in this talk. I'm going to consider series that have 2 parts. So in blue, I'm going to have an alternating part. Right, so there's a minus 1 to the n here, plus, minus, plus, minus, plus, minus, and a non-alternating part. And I'm going to try and keep this convention. Red is non-alternating, blue is alternating. And there was a clever reason for red and blue to do with magnets, but I don't understand it now. But these coefficients, an, plus and minus, are factorially growing. So what we're going to do is we're going to take this asymptotic series, it's not well defined as is, but we're going to define a new series, which is well defined, by taking each term of it and dividing through by m factorial. So we're just going to smash out this factorial growth. And we've got a series here that we can sum, has a non-zero radius of convergence. That's great, so we've completed this sum, but now we want to go back to our original series, and the trick is to use this expression for m factorial. So we can write m factorial as an integral, actually as a Laplace transformation. So if we Laplace transform back, we get an answer for this summation. So roughly speaking, what are we doing? We've divided by m factorial, but we're putting m factorial back in as an integral, and we're swapping the order of summation and integration. That's the black magic there. And this is fantastic. This works. This can give you a finite answer. But, and there's a big but here, and this is where all the interesting stuff happens, this integral here needs to be well defined. In particular, what do you do if the integrand has some cut or pole along the integration contour? And this example illustrates that. So I've done my Borel resum of the series. I've got a blue bit here. This has a pole at t is minus 2. Well, that's fine, because that's not in 0 to infinity. But the red bit has a pole at t equals 2. And that is, t equals 2 is on this contour. So this integral isn't well defined. So we have to do something. And the thing we're going to do is we're going to change the direction in which we integrate. So rather than integrating along the positive real line, we're going to integrate at an angle above the real line. So we're going to skirt around, go above all of these poles and potentially cuts and all sorts of stuff that can happen along this real axis. And since the function is nice, integrand is nice along this contour, we can do the integral. So that's great. But of course, you know, nothing's telling us to do that. We could have equally have gone below. And that would give us a prescription for the integral. So we've got an integrand that can depend potentially on the direction in which we're integrating. And indeed, as you pull this integration contour through the cut, you can get a jump. You can get a jumping phenomena. So this prescription gives us a finite but ambiguous answer. So we've gone from no answer at all to a finite but ambiguous answer. So the difference between integrating above the contour, above the cut and below is 2 pi I e to the minus a over g, something like this. So two factors here. First, pure imaginary. That's interesting. So the real part is non-ambiguous, but the imaginary part is. And there's a weight here, and it's the same instanton fugacity that we had before. And this is how the perturbative series is talking to the non-perturbative series. In fact, what's going to happen is the non-perturbative sector is also ambiguous. And it's ambiguous in a different way. It's not like you have to do a large order analysis. It's actually ambiguous at leading order, because you're looking at instanton, anti-instanton pairs. There's a moduli space that you need to integrate over, and that integration over the moduli space, some quasi-zero mode actually, there's a potential, is ambiguous, and you need a prescription to treat that integration. And what was shown by Bogomolny and separately Zinjastan was that this ambiguity here is exactly the same and opposite the ambiguity in the non-perturbative sector. So that's kind of amazing. You take this perturbative series that's badly defined, factorially growing, you add to it your non-perturbative piece that's also badly defined, but miraculously added together, the whole thing is well defined. And that's the idea of a trans series. Okay, and this has a very long history and a lot of recent work, and there is much more, and I apologize to names I've missed. Okay, so that's the sort of techniques behind resurgence. Any questions at that point?
Is there some theoretical explanation why it should be there? Why it should be the case?
Well, there's a physical thing, which is physics should be well defined, and my energy should be real. Okay, the mathematics, that's really murky mathematics now. This is Ekal's theory of trans series, which is not fully developed or understood. That you can add up all these potentially infinitely many divergent series to find a well-defined answer. Yeah.
I was just wondering, does it somehow miraculously always give you all the non-perturbative physics, or just the non-perturbative physics that you need to make the perturbative stuff?
Good. So this is a nice point. Okay, so the punchy resurgence conjecture is that the perturbative sector knows everything. Everything. That's quite punchy, and I'm not sure to the extent to which that's fully accepted. Here, for instance, the perturbative sector doesn't know about the one instanton event. It knows about the instanton anti-instanton event, okay? But it actually knows a bit more than that, because if you then do fluctuations on the instanton one anti-instanton event, that itself is an asymptotic series that resums, that knows about the 4 instanton event, which resums to know about the 6 instanton and so on, and that's all implicit in the perturbative sector. So the perturbative sector knows a lot. Okay, and that's this idea of a resurgence triangle. Okay, so look, I think this idea is beautiful, but there are many open questions. I think if you could expose the resurgent structure of 4D Yang-Mills, you would be you'd be a rich person. But before you can do that, there's quite a few things, which is, what about theories without instantons? What about when we're not really talking about quantum mechanics, but actual quantum field theory? What's happening with renormalization? How does that talk to these resurgent observables? Lots of other subtle questions about the role of complex saddles. In fact, this is particularly important in the context of gravitational path integrals and stuff like that. So there's lots of stuff going on here. And the philosophy here is that I can't do four-dimensional gauge theory, but maybe one-dimensional, 1 plus one-dimensional integrable models are a good place to start because they're calculable and they can share some interesting RG profiles. They can be asymptotically free, they can be confining. In fact, the theory I'm going to talk about is gapped in the infrared and completed in the UV with a CFT, which I think is kind of cool and maybe says something about physics. Okay, so I'm going to talk a little bit first about some older work. This was work initiated with Saskia a long time ago, but then also pursued with Lucas last year or the year before. And I reported this on the online version of this series. I know not everyone was there, but so I won't dwell on it too long. Where I've been considering Yang-Baxter and bi-Yang-Baxter type deformations of the principal chiral model. Does everyone know what a Yang-Baxter deformation is? Does anyone not? You're in the right room. Okay. So the strategy we're going to do here is we're going to try and find the equivalent of the instantons that can be related to these Borel poles. That's what our aim is. So to try and identify the classical saddles, or semi-classical saddles, that source the breakdown of perturbation theory. And we do this in a bit of an indirect way, basically as advocated by Alexei Mitat and probably some other people, Gerald. We're going to, instead of considering the quantum field theory in R2, we're going to reduce it on a cylinder with some twisted boundary conditions. It's like turning on a chemical potential. And the claim, and this is where I think there is a bit of hand waving, is that when we do this reduction, we're adiabatically connected to the theory on R2. We're not going through a phase transition, and we're kind of accessing enough information about the theory on R2 to be reasonable. And there's some evidence for that claim, but we'll take it. So we're going to reduce from the two-dimensional deformed principal chiral model to quantum mechanics. We're going to look at the large order behavior of that quantum mechanics, just like we did with the double well. We're going to find the Borel poles. There's a little trick here, a Borel pade. I don't know if I've got time to tell you about that. And when we found the Borel poles, we're going to pay close attention to their location, because the location of the Borel poles, that was the instanton action. And we're going to find instantons in the quantum mechanics that source these Borel poles. But even more, we're going to find genuine two-dimensional quantum field theory configurations, finite action saddles, which then fractionate into instanton, anti-instanton events when put on the cylinder. Okay, so please stop me. This next slide, the next slide is a 40-page paper on one slide, so I'm suppressing quite a lot of detail.
So why you should expect non-barrel non-summability? Why it can't be barrel summable?
Well, you can get Borel summable contributions, but typically just you can get an alternating piece, a non-alternating piece. You get what you get. You have to do the calculation to find out what you have. Okay, so here we go. This is this 5-step program I just outlined. So I'm going to consider here what's called the bi-Yang-Baxter model. This is a 2-parameter squashing of the sigma model whose target is a 3-sphere. So SU2 theory. I'm going to do twisted boundary conditions. So as I go around the circle, labeled by X, spatial circle, I'm going to twist by e to the I sigma 3. And I'm going to keep only the lightest modes. So I'm going to parameterize this matrix in some way and throw away heavy modes in the reduced theory to get a quantum mechanics with a particular potential. And it turns out the potential you get for this double deformed model is some elliptic potential. Okay, so there are two deformation parameters, one here and one here, and these are elliptic functions, so there's an elliptic modulus that also depends on the deformation parameters. So this is some particular quantum mechanics that's actually studied for fun anyway. Interesting side remark is it's related in some way to n equals 2 four-dimensional gauge theory with 4 flavors, nf equals 4. I don't know why, but there we are. Okay, so we've got this quantum mechanics, and then we can just do perturbation theory, WKB perturbation theory, or some variant of that, to work out the ground state energy. And because this is just put on a computer, it's a recurrence relation. You can crank it for as much as you want, and you get up to 100 orders of perturbation theory, no problem. Here's the first couple of terms. This is maybe for eta as a half and zeta as a quarter, or some random selection like that. But you can keep going. And these numbers start growing massively. So you need to set precision, numerical precision, 100-digit precision, and your Mathematica.
No, you have
Coupling G,
and the field G.
yes, that's not very good. G is H bar, right? So yeah, that's unhelpful. It's alpha prime, I suppose. But yeah, this G was the 2x2 matrix, and this G was the coupling. Apologies. Okay, so we get this series, and then we find the Borel poles. So we do our Borel transform, and we plot the Borel poles. And what's not so clear here, but I'll have to explain in words, is there is a cut here that is starting at the location of this red circle, and there's a cut here starting at the location of this blue circle. The one nearest the origin is normally the dominant thing. So there's an alternating and a non-alternating piece. Okay, this is just a quantum mechanics. So you can find instantons. And here's the instanton action. And it turns out this position of this pole varies as we vary the parameters of the theory. And the instanton action also depends on the parameters of the theory, and they precisely match. So that's great. So this really does match this location. The cut on the left is a bit harder to explain. That doesn't come from instantons. It comes from what are called complex instantons. So you need to consider complexified field space to identify these solutions. But they exist, so there are some complex field configurations, ones that you'd normally just ignore, but you shouldn't. And they source this cut. So that's just at the level of one dimension. But the cool thing is that this actually arises from a finite action solution in 2 dimensions called a uniton.
Dan, these complex configurations are still special in the way, in the sense that they give a real action?
Yeah. There's some magic there. Yeah, complex field configuration, but real action. Weird, but true. But I think there's various motivations for, if you're thinking of the path integral, you should really extend to a Lagrangian in a complex field space. And I think that's what this is telling you about.
Just to compare to something familiar, so if you suppose you take O3 sigma model, do the same thing. The potential will be what? Sine?
Sine.
Which will have also instantons, and will be quite similar story.
Yeah. Yeah, and I think for that one, if I remember right, the location of this goes off to infinity in the limit. So the cut on the left drops out, and you only have the real field configuration. That's quite right. Yeah, good. Okay, and so there are some 2-dimensional field configurations that degenerate to these. So that's really fantastic. That's resurgence in action. I'm going to speed up a bit. So I like that analysis, but it's limited. And the reason it's limited is we reduce to quantum mechanics. So how much did we really know about the full 2D QFT? That's one reason. And another reason we know that this analysis must be a bit crappy is that these instant-on actions, which involve the parameters eta and zeta, are not RG invariant quantities. So I'm not sure that this location of this pole's not RG invariant. This isn't RG invariant under the flow of the eta model. So I'm not really sure what this means at a quantum level, at a truly quantum level. So, you know, the motivation should be to look at a genuine 1+1 dimensional calculation. And we didn't really use integrability. I mean, I did, because I could find the solutions of the equation of motion. But I didn't really use integrability in the way that I'm going to. Okay. So what I want to do is I want to explore exactly this theory, but in 1+1 dimensions, no reduction. And we tried this for quite some time and we gave up, either for technical reasons or for physical reasons, I'm not sure. But we can make headway on a different model, which is easier and at least as important, possibly more important, and that's the lambda theory. Okay. So I'm now going to move on to the next part of the talk, where I'm going to briefly describe the lambda theory, and then I'm going to describe some of the techniques we use to analyze it. Just a quick show of hands. How many people know what the lambda theory is? Okay, so 50% of you. So if I don't explain a bit, 50% of you are screwed. So I will explain a little bit, but a little bit quick, so everyone's a bit screwed. Okay, so this is a deformation. It's an integrable model that deforms away from a Wess-Zumino-Witten model. Okay, there's a particular construction of the integrable model, which was introduced by Svetsos, which is a bit like doing a Busher procedure, something like that. And here's the action for the lambda model. So there's a Wess-Zumino-Witten current algebra model here with level k. And then there's a deformation term, which depends on a parameter lambda, depends on some currents due to the -1 dg, and some operator which has got some adjoint action. So it's some composite operator deformation. That's what it is. To understand what this means a bit better, you could consider small perturbations. So if lambda was small, we're just deforming, the Wess-Zumino-Witten model by two currents. For those of you who know what Wess-Zumino-Witten models are, J minus here is the wrong current, so this one acquires an anomalous dimension. It's not a marginal deformation. Or you can take lambda goes to 1, so big deformations, and you recover the principal chiral model, or in fact the non-abelian T-joule of the principal chiral model. Okay. But I think that's enough for now, is just to know it's a deformation of the Wess-Zumino-Witten model that preserves integrability. It preserves integrability. The equations of motion have a classical lax formulation. These were slides that Thomas sprinted through today, but I think they're the same. So the classical lax for the lambda model. And actually, even better, there's an exact S matrix description. So classical is good, quantum even better. There's a quantum S matrix, which can kind of be derived, actually. You can do a discretization. You get some spin chain. You can look at the excitations over the ground state of that spin chain, and you take a continuum limit, and you recover this S matrix. What you need to know about it is it's got two factors here. So this cross is actually a tensor product. One reflects some G group symmetry, and the other is like it's a kink S matrix. So it describes the scattering of kinks in a sine-Gordon theory, more or less. Okay, so this is some particular answer. And what we're going to use is yeah? Yeah, Q at root unity, maybe K plus dual Coxeter. Yeah, this is the RSOS S matrix. Okay. So what we're going to do in the last half of the talk is we're going to use this S matrix, which is an exact statement, to probe the theory. So what we're going to do is, just having the S matrix isn't enough. That's exact. I want a perturbative expansion of something. So what I'm going to do is I'm going to hit the theory, and I'm going to calculate the response to hitting the theory. So I'm going to hit the theory with some chemical potential. So there's some charge, some U1. I'm going to stick a potential for that U1, and I'm going to calculate how the free energy depends on the chemical potential. Okay, and this is a very old story, how to calculate the free energy of an integrable theory when it depends on a chemical potential. I'll often Legendre transform to the energy, so I'll switch between free energy F and its Legendre transform a couple of times in what goes on, but it's the same thing. So this goes back to the 80s. So Polyakov and Wigman showed how to calculate this quantity in terms of an integral equation. This is the TBA equation. So chi is, roughly speaking, some density of states. Chi is a density of states. B is the Fermi surface where this density goes to 0. So you have to determine B in terms of H. That's actually why this is tricky. And K is given in terms of the S matrix data. So this integral, this is a convolution with some kernel, and that kernel is the S matrix. Or more precisely, it's the derivative of the S matrix with respect to momentum or rapidity. Okay, and so if you can solve this equation, you can determine E and rho, and then you can Legendre transform and determine F. Okay, this is quite a nasty equation. Good luck solving that. And this guy did something I think is astonishing. It's one of the most technical tour de force papers I've read. Volin understood how to solve that integral equation to very large orders in an asymptotic expansion in 1 over B, or in H. Okay, and there were some technical tricks. I'm not going to go in much detail, but I'll just tell you what the strategy was. So instead of using chi, he worked with what's called the resolvent, and that just simplifies some equations. No big gain here, but it's nice. But he explored the equations in 2 limits. One limit is called the bulk limit. So we're always going to work at large B, but he's also going to look at large momentum. But he's going to keep the ratio of B and momentum fixed. So that's one limit. And you can just write down an ansatz based on symmetries of what this resolvent should look like. And there's a bunch of unknown numbers here, C, N, M, and K, totally unknown. You can take a different limit where you take B to infinity, but now theta minus B fixed. And you can write down a different ansatz in this limit. Again, depending on some numbers, Q's, that are unknown. So we've got unknown numbers C, unknown numbers Q, and a really nasty integral equation. But it turns out you don't need to solve the integral equation. It's sufficient now to take this ansatz, expand it towards the edge, and match these 2 expansions. And if you match these expansions, you get algebraic equations that determine all the C's and all the Q's. And you do this order by order in the chemical potential. I think this is a work of art. Getting it to actually work on a machine is quite hard, but you can, in principle, go quite high in perturbation theory. So we do this technique, and we compute 35 orders of perturbation theory. So 35 orders of a two-dimensional quantum field theory in perturbation theory. And we do it analytically. So all our results depend on kappa, which is actually k over n. And we find, eventually, the energy density has some expansion in a coupling. Little subtlety here, I do a change in what the coupling is to remove some logs. This is a nice trick, but not important. So this, we find an asymptotic expansion. Now you know the game. I'm going to say, I've got an asymptotic series. I've got to find the Borel poles. So that's what we did. Okay, we found the Borel poles. Now, because I don't have infinite orders of perturbation theory, we have to approximate this. So instead of a perfect cut, I have an accumulation of discrete poles. But you should view this accumulation of discrete poles as a cut. And again, we see this structure of alternating and non-alternating contributions. Actually, there's a bizarre feature that these red poles just disappear when kappa is an integer. That's funny. There'll be a reason for that. Okay. Divided by n. And the scattering kernel only depends on this particular ratio. And I'm in some subtraction scheme where I don't screw that up. Everything only depends on this ratio. And then it's the SUN. Lambda is gone. Lambda is not there. That's really important. The theory is, good question, the theory is gapped. Yeah? So the coupling lambda's flowing, it's becoming large, and then it's being dimensionally transmutated to generate a mass gap. And that's happening here. And then eventually, because we've divided through by rho squared, all the masses cancel. But this is in a massive theory. That's quite right. Yeah. So there's no lambda. Okay, so we found these Borel poles. So then the question is, can we guess what is the asymptotic form of this coefficients? And we, after a little bit of head scratching, we come up with some proposal for the asymptotic form that looks like the thing at the top. This is exactly what I told you at the very beginning. Alternating piece and a non-alternating piece, factorially growing, but also with some, I've been even a bit more precise. I've included some sub-leading terms and some other little bits and pieces that you need to include. And then we want to determine what this function a plus and a minus, which can depend on kappa, and little a plus and little a minus are. Yeah?
In electrodynamics, if you change the sign of the square,
Yeah.
with the same kappa, you take kappa to minus.
If you take kappa to minus kappa, I think that would be the effect of doing a summation in this axis. And you'd be worried about the ambiguity that comes from summing over here. Yeah? And indeed, there's this Freeman-Dyson point about that. Yeah, good.
There is a discrete symmetry of the Swansea model, which is visible at the level of lambda.
Yeah.
And lambda disappears, so in the dimensional transmutation image, how it looks like this discrete symmetry?
I don't know, but this pole here is at the same place as this pole here, so I don't know if that's related to it.
It's symmetry lambda goes to 1 over lambda or something
yeah.
like that. Is this one?
It might be. I'm not sure. It's a good question how that's Z2 is reflected. K goes to minus K. So right. So it probably is that this pole here and this pole here are at the same place. Probably. Thanks, Ben. Okay. So we propose some ansatz, and then what we do, we want to find the unknown functions. So here's a plot. The dots are the actual numerical data. And this was possibly one of the happiest moments of my scientific career. because at 2:50 I said to Lucas, let's guess the form of the function. Let's guess what it is. We'll give ourselves 10 minutes to guess. And our first guess wasn't right. And our second guess, all right, there was a bit of prior, was A minus had this particular form. And blow me, look, the blue line goes straight through the dots. 8 minutes it took us to do that. That was brilliant. And then I can talk about it. And also we have a prediction for the red one as well, which is a bit less good for reasons I'm not fully understanding yet. We also know what these A plus and A minuses are. They're just 2 kappa and minus 2 kappa.
So why the product is 1 or whatever?
Why is
Plus times A minus?
no? It's they are to do with the S matrix. They're obtained from the S matrix in some complicated way. I'll try and explain. The product isn't actually 1, no. Okay. So now we know what the asymptotic form is, and we've got some of these subleading as well, by the way. You can actually borrow sum this exactly, not approximately. And that's what we did. We now borrow sum exactly, and we find a piece coming from the non-alternating, which has a pole or a cut starting at 2, and from the alternating has a pole or a cut starting at minus 2. Pole or cut depends on the value of kappa. And then you can do the resummation. So now we can resum this series, and we can look at the ambiguity. So we're now going to calculate the ambiguity as we resum across the red dots. And we get a purely imaginary piece with some instanton-like fugacity term, just like we saw right at the beginning of the talk, with this A plus function kicking in. Okay, so now there should be some non-perturbative sector that this talks to. Okay, I'm going to skip rather than speed up. Oh no, I'm okay. All right. So we're going to change technique now. We've done all we can with the asymptotic expansion. That bit of the story is full. But we're going to go back to the beginning, and we're going to analyze the TBA system. But we're going to do it in a different way. And this goes back to seminal works of Niedermeyer and Hasenfratz, who determined the ratio of the mass gap to the cutoff in MS bar by doing this kind of thing. It's amazing work, beautiful work, and it makes use of what's called the Wiener-Hopf technique. So for those of you who don't know it, what we're going to do is we're going to Fourier transform. So all our equations before were in position space, and we're now going to transform to momentum space, omega. K is the Fourier transform of the scattering kernel. And it turns out we can factorize, after taking away a delta function, we can factorize this Fourier transform into 1 over G plus times G minus. And the critical point here is that these G plus and G minus have well-defined analytic behavior. G plus is analytic up the top, G minus analytic in the lower half plane. And if you use this factorization technique, and in particular, we're going to use this combination var rho, which is the ratio of G minus and G plus. That's a particularly useful little combination that crops up. If you use this factorization technique, turn the handle quite some effort. Zamenhof claims, but doesn't give the proof in his paper, but then you do your homework, and after a week you figure out what he meant. You can find that the TBA equations can be rewritten. And this looks really rather similar to the original TBA equation in that it's an integral equation. But the main difference here is now I'm integrating between minus infinity and infinity. And that makes life all the much better. So it's for some auxiliary function u, which is determined from this equation. And if I know u, I can now determine the free energy, because the free energy just depends on u. So you just have to solve this equation. Now, there was a paper about 9 months ago by Mourinho and collaborators, and I think this one's really good. A lot of respect for this paper, because it understands where this non-perturbative ambiguity comes from. So I'm going to sketch their argument. So we have to solve this equation for u. And we have to look at this integral. And there's an integration contour here, minus infinity to infinity. So here's a picture of what's going on. Here's rho. My integration contour is the green line. And I have cuts and poles on the imaginary axis. So what we do is we contour pull, right? We contour pull this integral to both sides of the imaginary axis. But this isn't very helpful because there's a cut and there are poles at the same place. So what we do is we're going to redefine where the branch cut is in the logarithm. We're going to move the cut off the axes. That's a choice. We get to choose that. And we can either put the branch cut to the left of the imaginary axis or to the right of the imaginary axis. Okay, and then our integral comes into two bits. An integration on both sides of the cut, so that's a discontinuity integral, and a finite sum of residues, or possibly infinite sum of residues. But there's two ways of doing it. And it turns out that the two different ways of doing this contour pulling give you two different answers. So everything depends on e to the plus or minus I pi kappa, where plus is to the left and minus is to the right, or vice versa. Okay, so this equation can now be analyzed order by order in e to the b, e to the minus b, which is our non-perturbative parameter. And we get a result. So you work through the algebra, and we find a result. So we find the first couple of terms of the perturbative series. Right, so this agrees with the first term of the full thing the computer found out, but we only go up to first order. But then we find the leading non-perturbative behavior here. And as I said, this leading non-perturbative behavior is ambiguous with plus or minus I pi kappa. So if I take the difference between our prescription of going to the left and the right of the cut upstairs, what we find is an ambiguity in the imaginary part of the energy density that goes like 2i a plus this function e to the minus 2 over gamma. In fact, this expression here, which comes from the non-perturbative ambiguity at leading order, precisely matches this expression here, which came from the numerical 35 orders, resummed, processed multiple times, etc. So what we found here is a clear evidence of the same cancellation mechanism we saw right at the beginning in quantum mechanics, this BZJ cancellation, and presumably this is the start of a full trans series in which all sorts of these non-perturbative ambiguities will cancel out. Okay, so I'll just say a couple of conclusions. I won't say all of these. So just to summarize, what did we do? We used modern techniques, and as a toy model, we explored these modern techniques using this lambda model, which is interesting because it's a UV CFT completion with a dynamically generated gap in the infrared, so that's kind of cool. We saw good evidence of cancellation between perturbative and non-perturbative ambiguities, which is to say the theory is well defined. Physics is not broken. You could push this much further, of course. You could look at subleading contributions. You could look, as you said at the very beginning, Emmanuel, at higher instanton corrections or higher non-perturbative corrections. Many things you could do. One thing that we haven't done and I don't know how to do it, is I don't know how to give a semi-classical field configuration that corresponds to these guys. I don't know what that is. So that's an interesting question. I think there was an interesting question raised by Ben this morning that I want to come back to, because, there was nothing tame at all in any of the functions I put up on the board. There were gamma functions all over the place. There were sine functions all over the place. This is a resurgent Chern series. But apparently it might be physically a tame function if we calculate that free energy density. So that's a nice question relating to this morning. I'd like to know the answer to. This was all done in the context of a massive theory. But if we're doing holography, we're interested also in massless, in string theories. So it'd be interesting to know if similar analysis can be done for massless theories. Or a slightly easier question may be there are integrable deformations between two different CFTs. So maybe you can do similar resurgence analysis here. And then I think there's other more exciting ways that might have relevance for gravitational physics to look at bulk boundary integrable systems and resurgence. And maybe, rather than doing this finite chemical potential, maybe you can look at the quantum spectral curve or something like that. Okay, so lots more to be done. As anticipated, I don't think I'm going to give you part 2 of this talk, so I'm going to stop there, and thank you very much.
Okay, thanks a lot, Dan, for the nice talk. We've got plenty of time for questions, and lots of questions over there.
Yeah, so thanks for a nice talk, Dan. So just to make sure that I understood this, where you had your plot with your points, and there was a slight disagreement on the red plot.
Yeah.
So this disagreement cannot be due to like subleading non-perturbative corrections or something,
Yeah,
right?
I think it probably is.
It is.
I think it probably is due to,
Okay.
to there being some other things in this expansion. I think it probably is.
Okay.
Yeah.
All right. Okay, good. Then
Yeah.
I'm also happy.
That's right.
And then another question, maybe I missed it, but at some point you mentioned your S matrix is actually a matrix, and in the rest of the talk you seem to mostly talk about a single.
Yeah, of
like,
course. I waved
kernel?
a huge thing under the carpet. So I'm turning on a particular chemical potential that selects for you certain states. So for instance, if you were doing this for the sine-Gordon theory, the chemical potential would just select out the kink-kink scattering and dispense the anti-kinks, and you would use that as your kernel.
Okay, but so then you're also working at large chemical potential or something?
Yeah, right.
Okay.
No, that's true. You are implicitly at large chemical potential. So you're making some assumption that throwing away those things doesn't impact the conclusion. That's true. And the other thing is, I'm just using the reduced TBA that has only one variable.
Yeah.
In principle, you might want to use this full TBA system with all of your fields.
But I guess for that there's no analog of Volin's analysis, right?
I think you would have to work quite hard. I'm not sure that it would be very tractable at all.
All right, thanks a lot.
Sorry, maybe you mentioned this, but I missed what, in terms of the difference between the lambda and then the Yang-Baxter, just one side Yang-Baxter, what is the technical difference that allows you to do it for the lambda but not?
I think the physical difference is that you have this UV CFT for the lambda model.
So what if you take the Yang-Baxter one side, it will just squash 3-sphere?
Yeah.
With the which has the UV completion.
So this ansatz just doesn't work.
Okay.
And I don't know why.
Okay.
And we've tried every possible variant of ansatz that you could think of for this bulk thing, which normally involves changing this to being a square root. There's something to do with bosonic and fermionic kernels. I'm not sure if that's relevant there. maybe you don't include this power, maybe you shift this power. You know, we've tried every permutation of ansatz that's possible, and we never made it fly, because basically this matching never worked for us. I don't know if there's physics, or we were thick, or what, you know, I don't know. On that though, because okay, it's a bit of a niche point, but yeah, the kernel, I don't even have it. The kernel G+ for the Yang-Baxter model is really beautiful. It's a really nice, simple thing. So it looks like it should work really easily in terms of Euler beta functions, but it didn't. So we gave up.
Do we have? Maybe I have just a brief question. I probably missed it, but you mentioned when you talked about the Yang-Baxter model that you hadn't really used integrability, and
No.
you were going to use more integrability, I thought, in the lambda model, but then
In the in
didn't
the
see
lambda
where.
model, this is all integrability technique, of course. But back here, when we were just doing this
Right.
reduction to quantum mechanics, I didn't really care particularly about integrability at all. The only place I think it kicks in is that this is a nice, pretty potential. This has got some nice meaning in gauge theory. And to be able to identify, to solve the equations of motion, to identify these field configurations, they were easy enough equations that you could spot the solution. So the working definition of integrability is you can integrate equations. In the working definition, we used it.
so you didn't even. I mean, you didn't need to know that it was integrable.
No.
It was just
Not for this
simple enough.
analysis.
In that
Not
sense.
for this analysis, exactly. Yeah.
Maybe just a comment about, you mentioned the tameness and the fact that you have lots of gammas. I mean, certainly I think Thomas mentioned this in his talk. You have ratio of gammas, so
Yeah, we've got
there's a
gamma.
good chance that this somehow makes them
I think
tame.
that's right, but I think there's something even before that point, and I was just speculating of this. Yeah, I'm going to go right to the end. Close your eyes, right. When we're doing integrable theories, we have axioms for the S matrix, okay? Factorization's the big one, that's what we're really thinking about, but there's also various analyticity properties that we place on it. But when you solve these axioms, you find that your S matrices typically do depend on gamma functions and ratios of gamma functions and stuff like that. And you do a little bit of work to remove some double poles, and there's some hand waving and stuff. But you satisfy these axioms, and you get this particular answer. Now, Thomas was saying that scattering amplitudes are tame. Therefore, S matrices really ought to be tame. So my response actually was, I wonder if these axioms imply tameness. I think that would be an interesting and precise question.
Okay, do we have some other questions? Otherwise, maybe I can just ask another very naive question about the whole Borel story. How many orders to perturbation theory would I have to compute to be able to start doing this Borel summation and
Yeah.
start seeing the non-perturbative effects?
Yeah, okay. That's a good question, actually. Obviously, the correct answer is enough. Okay. So what we don't have all the orders of perturbation theory. We only have 35. So what we do is we fake it. Okay, so we do our Borel transform series, but only including the first 35 terms. Now that has not got cuts or anything, that's just a series, that's nothing. But then we approximate that, this is just black magic, I have no idea why this works. We approximate this by the ratio of two polynomials. And that, if you expand this out, you ensure that the first few terms match, but then this implies the full branch structure. This technique works with surprisingly few terms. In the 70s, people were doing this for QCD, predicting predicting terms off 3 data points. So it's surprisingly powerful. 70s is too early. But people are doing this with very few data points. I think to get any useful accuracy for us, we found 30 orders. And let me tell you, you've not lived until you've seen a zeta 33 in your calculations. There you go.
Okay, then let's thank Dan again, and we've got a coffee break.